Hello, I'm Steve Vardaman, and this is the first in a series of short lectures or vignettes that will serve as an introduction to Stat 602 at Iowa State University, spring 2015, and additionally as an introduction to a set of slides about modern multivariate statistical learning that can be found on an Analytics Iowa LLC website. My intention in this series of introductory lectures is to cover what I'm calling Module 1 here, in addition to cover what I'm going to call Module 2. And for the students at Iowa State University, I'd also ask that you have a look at this set of slides that I made for a colloquium talk at Los Alamos National Lab for a talk in summer 2014. Although I'm not going to record that talk, the slides are also available. You can find all of these materials at analyticsioiowa.com. There's materials there, course materials, and in particular there's modern multivariate statistical learning course materials. The set of slides for the material that I'll be using here in these lectures, there's Module 1 and Module 2. There are, in fact, 49 modules on that web page. There's a set of course notes for Stat 602 that will be in flux as we go through the course, as I tinker with those things, but the most up-to-date version will always be on this website. And as I said, there is this set of colloquium slides is also posted on this Analytics Iowa website. So I commend that resource repository to you as we go through Stat 602, and also if you're just looking at this set of introductory lectures, that's where you can find the slides. Okay, so it's my intention here to, in this lecture, talk my way through this first set of slides, modern multivariate statistical learning. Here's an introduction. What we're going to be talking about is statistics for big data, statistics for quote-unquote machine learning, statistics for modern data analytics. The place that statisticians always pretty much begin is with a rectangular array of data. Data made up of cases and data representing or having values of variables. Typically, those variables are referred to as features in this realm. Sometimes the cases are referred to as instances. We're going to pretty much start with a scenario where one has n cases and has p, or sometimes p plus 1 variables. The bulk of the variables we'll call x's, x1, 2 through p. If we're doing a prediction problem, then there will also be a variable to be predicted, y, and so there will be in rows p plus 1 columns where the biggest part of this data matrix is the vector, or is the matrix of uh, uh, predictors or covariates. I'll try to stick to standard vector notation. So usually vectors will be column vectors, and so if I want to talk about the data for the first instance, we'll talk about this first row, and I'll write xi, or the ith row, I'll write xi, 1, xi2 through xip. That's a row. I'll make it a column vector by using a transpose. Most classical statistical methods are implicitly aimed at situations where data are scarce, where one is in the business of wringing as much information as one can out of a relatively small amount of data. It's also usually the case that in that context, the people are worried about quantifying how much information data give about parameters of a fitted probability model. This set of material treats cases where it is not true that both cap N and P are small, so at least one of N or P is large. And usually we have not so much fundamental interest in models, parameters, how much we know about them. We're more interested in some other aspects of the situation. Here's something that doesn't change as we consider analytics. We consider data analysis for quote-unquote big data. As in all of statistics, the basic objective, qualitatively speaking, is to identify, to describe, to make use of structure, simple structure, finding low-dimensional, low-order structure in a data array. That's the objective in this course, just as it is in any context where statistical methods are going to be employed. There's particular terminology, jargon that's going to be used here. It's jargon that is consistent with modern machine learning jargon. So we will talk about supervised learning problems as being ones in which there is a y. We started with x's and possibly a y. Well, when there's a y, when there's one of these variables that is to be predicted, we'll call it a supervised learning problem. One is in the situation of wanting to find a function of the inputs, the predictor variables, the covariates that approximates y well. This is typically called a prediction problem, where in cases where y is continuous or measured, where y takes values in some finite discrete set, the problem is typically called classification, or sometimes people call it pattern recognition. Those are quote-unquote supervised learning problems. Unsupervised learning problems, none of the variables is designated as one that needs to be predicted on the basis of the others. So typically not talk about there being y, they're just px's, And the objective is still to find structure. It's to find low-order interpretable structure in the data, but now not where any one of the variables is designated as somehow more important or to be predicted on the basis of the other. And standard versions of this, clustering, principal components analysis, multidimensional scaling, these are quote-unquote unsupervised learning methods. Methods where we're looking for structure, but there's no single variable to be predicted. In supervised learning contexts, we will typically call the data array, the n by p plus 1 data array, we'll call it the set of training data, and I'll typically use T to stand for that set of training data. Question arises then: what are the new issues? What's the news here? Well, one thing that happens is that if one is going to deal with quote-unquote big data, sometimes there are computational limitations. Computing time, computing memory are finite, and that sometimes makes straightforward implementation of standard methods practically impossible. If I can't hold all of a data set in memory at once, that means I have to do computations in a different way than if I can hold all data in memory at once. Frankly, these computational issues are ones that are not going to be very much considered in these slides. They're not things that I know much about or really care much about. They're important, but they're just not things that are going to be much discussed in this set of notes. Things that are going to be given very much attention here are these issues. There is the fact that one faces in big data contexts the quote-unquote curse of dimensionality and the possibility of overfitting. The curse of dimensionality is a way of talking about the fact that if you have many variables, if P is big, and you're talking about measured variables, particularly when you're talking about measured variables, you're talking about points in P space. And P-dimensional Euclidean space is just huge. And the number of data points required to fill up even what one would think is a fairly small part of P space is just way beyond anything that intuition would point to. And what that ends up meaning is that essentially any data set with a large P is going to end up being sparse. One doesn't have very much data, even if one has 500,000 cases, if P is 100. Further, the potential complexity of functions of P variables, that is, how a response could vary as a function of P different inputs, just explodes with P. In addition to that, there is the truth that when P is large, one is essentially guaranteed that if one uses a method that is highly flexible in terms of the relationships that it describes or permits for relationships between variables, one's going to find a relationship, whether or not that relationship is real, whether or not it's reproducible, or whether or not it's reproducible or not. You take those notions together and you get the so-called curse of dimensionality. Related to that is the fact that if one has a sparse data set, which one almost always does have in modern analytics problems, because one wishes to deal with large P, one really ultimately does not have adequate data to support the use of highly flexible statistical supervised learning methods, and that can lead to so-called overfitting. Overfitting means that what appears to be a strong pattern in a sparse training set just doesn't hold up when one tries to apply a fitted method to prediction outside the training set. One needs to think about how in the world then can one approach this kind of problem. And a standard way of then choosing among various statistical procedures for a given data set is to find a measure of estimated or predicted performance and a measure of complexity for statistical methods, and try to optimize by varying complexity predicted performance. Now, that business of predicting performance in light of this notion of overfitting means that you can't really assess performance on the data set used to do the fitting of a method. Rather, almost always one has to employ some kind of a holdout sample. One fits on one set of data, assesses performance on another set of data. So that's the way, in rough terms, this issue of overfitting is addressed. We'll say a whole lot more about that as this course goes on. It's also important that I say some things about upfront work in predictive analytics before going any further. We began with this rectangular data array. It's important to say that in real predictive analytics problems, the reduction of everything that's known to this n by p data array is an essential and highly critical activity. It's an activity that can take in terms of person hours, the bulk of one's person hours applied in a real project, and it has to be well done. One needs a reduction of the available information that doesn't miss things, doesn't squander information, but does that representation in as simple a way as is possible. If one fails to encode in that data array all that is knowable, then one limits the ultimate effectiveness of one's statistical analysis. If one simply makes too big a data array, then one is in the context of looking for a needle in a haystack. So this is important stuff. It's upfront stuff. It's essential stuff, and it has to be done before the formal technical subjects in these modules or in these lectures come into play. It's interesting, I think the phrase data mining in many contexts really refers not to any kind of processing that's done of such a data array, but rather to this upfront development of plausible feature vectors. Another thing that needs to be said up front is that in a typical analytics problem, the variables, that is, the x's in a data matrix, are very often, when one starts, in different units. One might be in a voltage, one might be a temperature in, say, millivolts or degrees Kelvin. And in some kinds of analyses, that's completely fine. But in others, it doesn't. That's not fine. In situations where one is going to use distances between data vectors or inner products between data vectors, the units used matter, and one gets fundamentally different results depending upon the units that are employed. One surely doesn't want ultimate predictions in a supervised learning context to depend upon the units involved. And just in terms of fundamental logic, I mean, what does something like this, which could be, say, a squared or a distance between two data vectors, what in the world does that mean? What's the square root of volts squared plus degrees squared mean? It doesn't mean anything. So a natural approach to this is to begin by standardizing predictors, standardize x's, and centering y's if one is going to use a methodology that depends upon inner products or distances. That is, to take a variable and subtract its mean in the data set, divide by its standard deviation in the data set, and to take a response and subtract its mean in the data set to make new inputs and responses, and then do analysis on standardized x and centered y, and then to ultimately undo those transformations to make inferences or make conclusions on the original scale.